everyone. Our first speaker of this afternoon session is Professor Wright from Columbia University. He will be presenting on a geometric analysis of phase retrieval, actually for which he received the Frontiers of Science Award. Professor Wright is a renowned expert in the field of applied mathematics and signal processing. He has made significant contributions to sparse representation, low rank matrix recovery, and high-dimensional data analysis. So let's welcome Professor John Wright.
All right, so thank you so much for the kind introduction. Thank you, everyone. Thank you to the organizers. This meeting has been fantastic. This is one of the best conferences I've ever attended. So it's really, really wonderful to be here. So I'm going to talk today a little bit about this paper and also a little bit of a broader picture around some ideas on optimization, in particular, optimization in the absence of convexity. Are we on? There we go. Okay, thanks. Okay, so everything I present today is joint work with these two former students. So Ju Sun, who's now at Minnesota, Qing Xu, who's now at Michigan. I'll also mention work with a number of other students and collaborators along the way. Okay, so optimization. I know we have some optimizers, some applied mathematicians in the room. So it's a kind of funny time to be doing optimization in the sense that as a society or almost as a civilization, we're investing absolutely incredible resources in solving optimization problems, right? So it seems like every month you hear a new announcement, some company is investing more and more in computation to solve large-scale learning problems in machine learning, AI, et cetera. So we're doing a tremendous amount of optimization. And the kind of funny thing is that at least if you take a worst case perspective, the kinds of optimization problems that we encounter, whether it's in deep learning, representation learning, whether it's in computational sensing, from a kind of worst case perspective, these are optimization problems that maybe we shouldn't be able to solve to any particular guaranteed quality. So, when I started working on optimization, generally as a graduate student, the picture kind of looked like this, right? So it's like you had the problems that you believe that you can solve in a strong sense. So these might be, convex problems with a little bit of additional structure, and then you have everything else, right? And so what you do is you work really, really hard to get your problem over here. You try to deploy all available resources, all available cleverness to get a formulation that looks like this, because this is something that I know I can solve, right? And then, there's decades of technology that gets me from here down to here with guarantees and guaranteed efficiency. And, right now in optimization, many of the most interesting problems sort of fall in this category of everything else, right? And this everything else category, non-convex optimization, is in some sense a complement of a well-structured thing, right? So this is, in some sense too big. We have some kind of basic obstructions to finding good solutions, right? We know that it's easy to make examples of objective functions where local methods get stuck. It's also easy to make examples of objective functions that are so flat that it turns out to be NP hard to find a good direction to improve your situation. So, in general, this kind of complement of convexity is not a very well-structured thing, and we shouldn't have very much hope. On the other hand, there are a few non-convex optimization problems that we're able to solve in a strong sense, right? So, I believe I'm speaking to a room of applied mathematicians. This is one non-convex problem that, as an applied mathematician, one solves on a very, very regular basis. And this is the problem of optimizing a quadratic function over a sphere. Okay, so I have a symmetric matrix A. It has a complete orthonormal basis of eigenvectors. For simplicity, let's imagine the eigenvalues are distinct. And what I want to do is to minimize x transpose AX such that norm of x L2 is equal to 1. Okay, and then, if you just scribble a couple lines, investigate this problem, what you can see is that actually for this quadratic form over the sphere, the critical points of this quadratic form end up being the eigenvectors of the matrix A. Okay, and of course, as we all know, the global minimizer here is the eigenvector with smallest eigenvalue. The other critical points are eigenvectors with bigger eigenvalues. And if you do a little bit more calculation, what you can see is that at all of those other critical points, there are directions of negative curvature. In particular, the index of these non-minimizing critical points turns out to be the index of the eigenvalue minus, and it turns out to be n minus the index of the eigenvalue. So if I'm at the second eigenvector with second smallest eigenvalue, I have one direction of negative curvature. Third smallest, I have a two-dimensional subspace with negative curvature, and so on and so forth. Okay, so this is one example of a problem that somehow sits over here, but on the other hand, we can solve in a very strong sense, right? And so the particular structure here is that, as it turns out, local minimizers are global, right? The only local minimizers are the smallest eigenvector and it's negative. And all of the other critical points have strict negative curvature. So I sort of know I'm not going to get stuck. Okay, so that's nice. And in some sense, at like a very basic geometric level, you can sort of look at this as a reason why numerical linear algebra is tractable, right? Underneath our eigenvector decomposition, our singular value decomposition, we have this core non-convex problem that happens to be globally well structured. Okay, so that's really nice. Now, it turns out that there's a connection between optimizing quadratic forms and data analysis, which is that if I'm trying to find a good representation for a data set, well, the most basic technique for doing that is principal component analysis, right? PCA. What do I do in PCA? Well, I write down the covariance matrix of my data set. So that's a positive semi-definite matrix. And I look for some directions that maximize that quadratic form. So I optimize that quadratic form over the sphere. Okay, so this is an example both of a simple problem in numerical analysis that I can solve globally, also a very, very simple data analysis strategy that has under the hood non-convex optimization. Okay, so this is one that we're fortunate enough to be able to solve. Okay, so the topic of the talk is going to be looking at a couple other non-convex problems that we're fortunate enough to be able to solve. And our entry into this kind of direction, let's see. Oh, okay, it's catching up. So our entry into this direction, myself and Ju and Ching and some of the other students, is actually through another core problem in data analysis. And that's the problem of finding concise or sparse representations for data. Okay, and this is kind of the problem in signal processing, right? I have a family of signals. I would like to concisely approximate them. And classically, the way that we did this is with the tools of harmonic analysis. So, what we would do, from the 1800s through the 1990s, is we would think about classes of functions, classes of signals. We would think about representations that are maybe optimal or near optimal for those classes of functions in terms of their decay properties. And then to the extent that natural images follow those assumptions, if I deploy those representations, I get good algorithms for compression, for denoising, for super resolution, so on and so forth. Basically, I can do all of signal processing if I have a good representation. Okay, so up through the 1990s, a lot of signal processing is driven by this kind of beautiful connection with harmonic analysis, where we're designing good representations for signals, and then we're deploying them to solve problems. Okay, and so around the mid to late 90s, some kind of brave and forward-looking people started to ask, well, we're starting to collect data sets with more and more signals. Maybe not ImageNet size, but we have some things. Maybe it's possible to start learning representations from data. So maybe instead of hand designing my data representation, I'll sort of collect a big set of data, and then I'll ask the data to speak for itself. I'll ask for some kind of an orthonormal basis that maximally sparsifies that given set of data. Okay, and this has a lot of motivations. There are neuroscience motivations for this. It turns out that if you go to do this, in a lot of situations, you get basis functions that look like the receptive fields early in the human visual system. They also look like the early filters in a convnet, so there's probably some connection there. And as it turns out, if you go to do this, because data have a lot of intricacies that are a little bit hard to model, you'll typically do better learning from data than working with some fixed representation that comes from some kind of more abstract function class. Okay, and so there are a bunch of lists of the pioneers of this kind of approach at the bottom of the slide. People like Michael i.i.d, Julian Meiral, so on and so forth. This particular basis is from a paper of Meiral, i.i.d, and Shapiro in 2007. Anyway, the point is that it started to become clear that we can learn very effective representations from data. And so then there's kind of a question that comes from this discontinuity here, because this feels, while limited in its expressive power, mathematically very well justified, right? We're sort of doing respectable stuff. And now here it's a little bit less clear, right? In particular, it's less clear how much data is enough. It's less clear when my algorithm will spit out a representation that will generalize. It's just a little bit less clear what's going on, right? There are a lot of questions. Okay, so in the first couple minutes of this talk, I'm going to talk briefly about a problem in representation learning, so in dictionary learning. This is kind of the prelude to the phase retrieval portion of the talk. That's going to be the second half. And the reason that I'd like to talk about this one first is that these works kind of bookend each other in some ways. We'll make that clear a little bit later. And also, a lot of the intuitions from here are actually deployed later on. Okay, so, dictionary learning, what is it? Well, the idea is that we have some data. We would like the data to sort of tell us a good representation, right? We'd like to go from data to a dictionary. And in a lot of signal processing, good means accurate. I want Q, my basis matrix, times some coefficients to be close to Y, so accurately reproduce my data. And I want my representation to be concise. I want it to be sparse, right? Because typically it's the sparsity of this representation that gives me compression, denoising, etc. Okay, so as a math problem, this is just a matrix factorization problem, right? I have some data Y. There are columns of a big matrix, big Y. The data dimension here is little n. The number of data points is big N. And what I want to do is approximate it as an orthogonal thing. That's the basis that I'm going to learn, times some sparse coefficients. So right, Y is Q times X. Now, we mentioned earlier that this is kind of a talk about nonconvex optimization. And there's sort of a really basic structural reason why this typically is nonconvex, which is that there's nothing in the problem formulation that tells me what order I should put on the columns of the dictionary. So if you work really hard and find me a good representation, Q1, Q2, Qn, well, if I go ahead and permute those columns, I'm going to get an equally good representation, assuming I make the corresponding permutation on the rows of X. Right? So there's kind of a symmetry here. And because of that, unless you work really hard and are kind of really clever, you're going to end up with a nonconvex formulation, simply because any formulation that involves optimizing over the dictionary and the coefficients is going to have a minimizer for each of these signed permutations of the best solution. Okay, so kind of simple model problem, and then it turns out that often this ends up nonconvex when we phrase it as an optimization problem. Okay, so around 2010 or so, people started getting seriously interested in this question of what does representation learning do, and when can we guarantee the performance of the algorithms? And again, there's a big question because the kind of bread and butter methods here are based on nonconvex optimization, often some kind of alternation between the dictionary and the coefficients. And a priori, it's number one, not clear how well they work in general, and number two, very unclear how much you could say about it. So one thing that you can try to do here is you can try to kick out the non-convexity somehow. And to do that, you have to break symmetry in this model. You need some way of ruling out this one and leaving this one. Okay, and so what I've kind of listed here on the slide is one approach to doing that basically uses some amount of cleverness to prefer certain solutions over others. And I won't go into too many of the details here, but basically, if you're kind of sneaky about how you do this, you can phrase this dictionary learning problem as a sequence of linear programs. So you can solve a sequence of linear programs, each of which is sparsifying something, but subject to a constraint that tries to break the symmetry. And if you sort of look at this in a kind of model scenario where you imagine that there's a true dictionary and some true coefficients out there in the world, and your job is to find them, then if this representation is really, really sparse, it's actually possible to make this work. So it's actually possible to solve this representation learning problem by linear programming. And in particular, there's a formal result of this nature that's joint with Dan Spielman and Wen Wang from 2012. And what it says is that if this X natural is a sparse random matrix, meaning that the entries of x natural are on with some probability theta, and when they're on, they're Gaussian. Then if theta is about 1 over the square root of the dimension, so pretty sparse, this kind of thing will succeed. Actually, by solving the sequence of linear programs, you'll be able to find all of the columns of Q. Okay, so to some extent, this represents an attempt to avoid non-convexity by being clever, by sort of chopping things up. And again, you can prove things. It works in some pretty idealized scenarios. On the other hand, you can show for this approach that when the sparsity rate exceeds 1 over root n, meaning that your target representation is not super sparse, this thing breaks. Okay, and so, you know, via a sequence of steps, this is going to lead us to phase retrieval. And the sequence of steps is the following. So together with Jusun and Qingchu and some other collaborators and students, we spent some time thinking about how to break this barrier. Because from a sparse recovery perspective, what this says is that the method kind of works in the ultra-sparse regime. It works in like the most idealized regime. And it turns out that this is kind of intrinsic to this approach. You can't break it with this or other things that sort of look similarly clever. And so, you know, after banging our heads against it for a while, we decided to kind of as a last resort, just go back to non-convexity. So, you know, in some sense, let's follow what the pioneers of the field have been doing for a while now. Let's take non-convex optimization, let's throw it at this problem, and let's see what we get. And again, kind of the thought is that probably it'll also be subject to this barrier, then we'll know that nothing works, then we can give up and do something else. That's kind of the thought. Okay, so what I want to show you is an experiment that, you know, at least for me, made me sort of change the way that I think about optimization and non-convexity. So in this experiment, we're looking at the dictionary learning problem. So, you know, again, we're factorizing y into q times x. Q is orthogonal. We want x to be sparse. And instead of being clever, we're just going to write down a big optimization problem. Okay, so we have a cost that measures everything I want in the problem, my fidelity to the observed data, the sparsity of my coefficients x. We're going to optimize that over the orthogonal group by some kind of a local method. We can talk about the details, it doesn't really matter. And we're gonna see what happens. Okay, and so for this problem, this is what happens. So what I'm plotting here are objective values as a function of iteration for a number of distinct random initializations. So, you know, here I'm learning for this particular image. This turns out to be what the optimal dictionary looks like. The Golden Gate Bridge, you've got some like vertical structures that capture these things. You've got some other structures that capture that, so on and so forth. And, you know, from optimization perspective, what we can see is that if I take distinct random initializations, I somehow always get a solution with the same objective value, right? So they always converge to this value. And, you know, this, we found a little bit surprising. We kind of weren't expecting this, but this turns out to be actually a very robust observation. So here I've plotted 8 runs, but if you do 8,000, you'll always see it. If you change the Golden Gate Bridge to the fish or some other image, you'll always see it. So, you know, somehow, at least for this problem, not for deep learning, but at least for this problem, there's something structural going on that's allowing us to solve the problem, right? This is, you know, not just like we try and hope, but, you know, somehow there's something really happening here. Okay, and so that felt like it deserved an explanation. So here's a kind of attempt at an explanation. Okay, so to attempt an explanation, what I'm going to do is I'm going to look at this objective function, which again contains sparsity and data fidelity. I'm going to manipulate it a little bit, and I'm going to try to visualize it in a very sparse, so kind of idealized, very sparse and low dimensional setting. Okay? So my variable of optimization here is an orthogonal matrix Q. I'm going to marginally minimize out over the coefficients x. Turns out that if you minimize an L1 norm plus a squared L2 norm, you get something that looks like an L1 norm that's kind of rounded out at the bottom. This is the Huber function, you know, if you like statistics. And so it turns out that in this setting, this objective function is equivalent to minimizing the Huber function, this kind of rounded out L1, on Q transpose Y. So it's like basically sparsify the coefficients of the data in this dictionary. And if the problem is low dimensional, then what I can do is I can actually sort of decompose this over the columns of Q, right? So each column is one of these little bases that we're finding. And I can plot it as a function of one of those columns. All right, and so in this kind of idealized situation, this is what it looks like. So here, color represents objective functions. So yellow is big, blue is small. The red points are columns of your target representation. So you can see the sort of symmetry that was in the original problem is kind of reflected here, right? We have all of these equivalent solutions. And what you can see is that although we have many different good solutions in the space, somehow there's a nice global structure, at least in this picture, to this objective function that lets me be pretty confident that if I started right here, I would get, yeah, maybe to here, but I'm going to get to one of the red points. So, you know, instead of being some kind of a convex function, I actually have a structure that visually kind of looks piecewise concave, right? Piece, 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 piece. So a priori, I don't know which equivalent solution I'm getting to. I may end up with a reordered version of the dictionary, but I know that I'm going to get to one of them. Okay, at least if we believe the picture. All right. And so it turns out that in some settings, you can actually prove that this is the case. There's a kind of fun geometric intuition that sort of explains why something like this might be true. So the geometric intuition is that you're sort of trying to sparsify something. You're minimizing an L1 norm. L1 norm is piecewise linear, and a positive linear function over the sphere turns out to be geodesically concave. So actually, in the ultra-sparse situation, this picture that somehow this is a symmetrization of a concave function turns out to be rigorously true. Okay, and then for signal processing, you know, you kind of want this to be true not just when the problem is super sparse. So for that, you need to do a little bit of a probabilistic analysis. You need to argue that this structure maintains even when your target is a moderately sparse random matrix. This is a little bit delicate because the problem is non-smooth, and so you sort of have to be careful about the pointy parts. But this can be done. Okay, and so what you're able to prove is that for this dictionary learning problem, there's a way of phrasing the problem, at least the problem of finding one column of the dictionary, as an optimization problem over the sphere that has the property that every local minimizer is good. Every local minimizer is close to a true column. And all of the other critical points have strict negative curvature. So neither of the bad things happen. Okay, and you can prove that when this target representation is only moderately sparse. So somehow just doing the natural thing, having a non-convex formulation, as long as you analyze it appropriately, actually does much better than sort of our best efforts to manipulate the problem. Okay, so this was a phenomenon that we found kind of interesting. You know, again, for me, a priori, I was not expecting to find something like this. You know, I sort of have the feeling that this kind of non-convex matrix factorization, let's see, there, you know, is just a sort of try and hope kind of thing. But what this says is, at least in certain cases, there seems to be something like structurally nice about it that makes it tractable. Okay, and so this is in this paper with Zhu and Qing. We were able to give a kind of partial mathematical explanation for this. And based on this, you can provably recover the dictionary. You can sort of do everything that you would want in the problem. Okay, so this was kind of interesting, at least for us. And it made us ask a little bit, what are some other non-convex optimization problems that might have similarly nice structure? You know, are there other situations where this kind of thing happens? And that you know, kind of has been a topic for the community over the 10 years or so from 2015, when there were a few papers on this. You know, there's this one. There's also a very nice sort of simultaneous paper by Rong Ge and collaborators on tensor decomposition that sort of say, okay, at least for a few simple non-convex problems, we can actually analyze the landscape of the problem globally. And so, you know, here's a list of some problems where people have done this. They include things like certain deconvolution problems, certain low-rank recovery problems, synchronization, community detection, so on and so forth. The paper that is the title of the talk, now half an hour in, is about this problem of phase retrieval. So this is a problem that I was introduced to via the students, and you know, I think Zhu and Qing were introduced to via a very beautiful talk of Emmanuel Kenda's, talking about this kind of phase retrieval problem. This is a very fundamental problem in signal processing, imaging, etc., that basically shows up because there are a lot of situations where it is easy to measure the magnitude of a complex signal or of an oscillatory signal, and hard to measure the phase. And the reason for that is simply that if I have a signal that is wiggling very fast, to measure its phase, I kind of need to measure it with something that also wiggles very fast, right? I need very high temporal precision. On the other hand, if I want to measure its magnitude, I just need to integrate the energy. So somehow, from a physical perspective, it's often a lot easier to measure the magnitude than it is to measure the phase. And the way that this shows up in astronomy, communications, imaging, microscopy, etc., is that there are all kinds of interesting measurement modalities where I have some, you know, tiny object that I would like to image, and what I'm able to see of that object is something like the magnitude of the Fourier transform of its sort of density of occupation in space. So, you know, in this diffraction imaging, I have my biomolecule, something like that. I hit it with a laser, diffraction occurs. If I put a detector a sort of certain distance away, follows from Fourier optics, then what I see at my detector is actually the Fourier transform of the occupancy pattern of this object. Because, again, it's hard to detect phase, what I get is just the magnitude. maybe I get a very noisy guess at the phase, but usually just the magnitude. And the phase retrieval problem asks me to go from that magnitude Fourier transform back to the original signal. Okay, so that's the phase retrieval problem. Now, just like the dictionary learning problem, this phase retrieval problem has certain symmetries, right? So if I take my signal x and I phase shift it, this magnitude doesn't care. If I shift it in time or space, this magnitude doesn't care. Also, if I conjugate flip it about the origin, this magnitude doesn't care. So there's kind of a rich group of symmetries of this measurement model. Okay, and that turns out to be the major challenge in solving this problem. So the Fourier phase retrieval problem, where my measurement is magnitude Fourier transform of the truth, is kind of a problem that notoriously sits at the edge of easy and hard. It's ill-posed in general in one dimension. It's well-posed for almost all two-dimensional x's. There are some classical methods. In some situations, they work quite well. In other situations, they experience bad local minima and need a lot of human intervention. So this is hard. So our paper doesn't actually address this problem. Our paper addresses a kind of easier version of the problem that's motivated a little bit by some other measurement models that people have cooked up. So, in different areas of imaging and signal processing and so on, people have looked at different ways of taking these magnitude measurements that give us, in some sense, richer information about the sample. So, one way of doing it is to introduce this random mask and take a couple of measurements with different random masks. Again, now I have magnitude Fourier transform of some different linear transformations of x. So kind of this mixed spatial spectral measurement. Another way to do it is if I have a two-dimensional sample to take a little aperture and kind of raster it around. So take the magnitude Fourier transform of there. If you're a signal processor, you recognize the result as the magnitude short time Fourier transform. And these are just a couple of examples. There are a bunch of different, very creative ways of taking other types of measurements where you're still constrained to a magnitude, but you're a little bit clever about what you do first. And often these generalized measurements make the problem fundamentally easier. In particular, in this kind of symmetry group, these generalized measurements typically get rid of the shift and flip symmetry. For example, if I think about my random mask is not shift invariant. Likewise, because I'm taking measurements at different locations, I now am sensitive to shifts. And so these portions of the symmetry group go away. And what I'm left with is only a global phase ambiguity. So it's kind of a friendlier model. Okay, so in general, the so-called generalized phase retrieval problem is the following. I see some measurements which are related to my target signal in the world by taking the modulus of some linear transform of that target signal. And what I want to do is to recover the target signal. So I want to go from these y's, which are magnitude of a adjoint x, back to x. Of course, just like in dictionary learning, recovery here is only up to symmetry, which here means we want to recover up to a global phase. Okay, so that's the generalized phase retrieval problem. Now, and it turns out compared to the Fourier phase retrieval problem, this one is a lot friendlier for nonconvex optimization. So, one natural thing that you could do if you, want to find an x that fits these measurements is to say, well, I'm going to go ahead and minimize, some function of the mismatch between A adjoint Z and Y. And, one very natural one, which is nice, it's smooth, differentiable, etc., is to just take the squared magnitude of A transpose Z, subtract it from the squared magnitude of Y, and then square the result, right? So this is 0 if we have perfect agreement, and otherwise it's big. Okay, so that's kind of a natural non-convex formulation. And just like we did earlier for dictionary learning, we might hope that if this collection of measurement vectors is rich enough, then this one has some kind of good geometry, right? Turns out that this thing is non-convex because, in some ways, because of symmetry. Also, as it turns out, there are some other critical points. There's this family of critical points that are orthogonal to the minimizers. So there's a little bit going on in the optimization landscape. But still, there's hope. Okay, so in the paper, we analyzed this under a kind of idealized model that a number of people were looking at around that time, where these AIs are modeled as random vectors. Okay, so the AIs are just independent, standard Gaussian random vectors. Now, that model is pretty idealized compared to this and this. It does at least empirically capture some qualitative features of these. And actually for these and other models that are more structured, people have been able to, using more powerful mathematical tools, analyze them, prove things about the optimization landscape, so on and so forth. But for this paper, we took kind of the simplest and the easiest model, which is just to make these A's be these kind of generic vectors. And so then, what we're hoping for is we're hoping to be able to show that this thing will give you the right answer when the number of measurements is close to the number of degrees of freedom in your target, right? This is a sensing problem. We don't want to use too many resources. So here we're hoping to recover x natural up to phase when the number of measurements is about n, the number of entries in x natural. Okay, and it turns out, just like we saw for dictionary learning, if you take this one and you throw gradient descent at it from different random initializations, you tend to always get good answers. And, again, there's a kind of intuitive geometric explanation why. Here we have our equivalent solutions. Here's a different slice of the space with those equivalent solutions. We have a maximizer in the middle, that's at 0. We have a couple of saddle points. There's actually a family of them. And what you can prove is that when you've seen enough measurements, actually, this is how the landscape looks. So you can prove that a kind of higher dimensional version of this obtains. And in contrast to what we discussed for dictionary learning, here analyzing the kind of expectation of the objective function with respect to the random measurements is an easy part. Actually, because it's a degree 4 polynomial, this ends up being a degree 4 polynomial. Not too hard to figure out what's going on there if you sort of, work with it a little bit. The kind of technical challenge here is achieving optimal rates, meaning showing that we have good geometry even when the number of measurements is close to the number of degrees of freedom in the signal. Okay, and so that needs, that needs a little bit of cleverness, a little bit of analysis, in particular because this objective function as a sum of random variables is somewhat heavy-tailed. It's degree 4. Okay, but one can do it. And so, what we showed in the paper is that when these measurement vectors are complex normal vectors and the number of measurements is about n log cube n, then with high probability, every local is good and the non-minimizing critical points have strict negative curvature. So, basically you get everything that you would like. Okay, and I think I have 0 minutes remaining in the talk, so I won't go into too much detail. There's a lot of high quality work in mathematical signal processing, imaging inverse problems around phase retrieval. Prior to this work, people were looking at semi-definite programming, nonconvex with initialization. What this showed is that, in some sense, there's an underlying nice geometry that, explains why you can do nonconvex optimization here. Since then, people have improved the number of measurements. There are some nice papers of Jen Feng Tsai and collaborators that get it down to n log n and then to O of n. And beyond that, it sort of turns out that there are these particular families of problems where some version of the thing that we're discussing in this talk happens. So these are problems involving phase ambiguities, synchronization problems, certain matrix recovery problems. There are also some families of problems that look kind of like the dictionary learning problem. These are problems with discrete symmetry, things like tensor decomposition, deconvolution, so on and so forth. So, in mathematics, usually we like a general theory. In the absence of a general theory, what this is showing is kind of a zoo of examples where people have been able to analyze particular problems in some amount of depth and sort of prove that the landscape is favorable. In particular, in a lot of these problems, the main sort of thing that shapes the landscape is the symmetries of the problem. So, that's kind of the theme of the talk, and again, the theme of the paper with Zhu and Cheng. There are a lot of open questions. There are some really beautiful optimization phenomena that we don't know how to think about. I haven't talked much about methods, but there are a lot of implications on methods. There are also a lot of questions about sort of worst case versus natural functions and how gradient descent behaves. And so, it's a big area. There's a lot that's kind of unknown and a lot to do. Okay, so with that, I just thank you for sort of bearing with a kind of rapid talk through a couple results around this theme of nonconvex optimization. Thanks to the collaborators, again to the organizers, and to all of you for your attention. Thank you.
Hello. Thanks for Professor's excellent talk. And any question from the audience?
Yeah. Hi.
Sparse recovery on the Fourier measurements. I just wonder, for your main result on the Gaussian measurements, what can you say about the Fourier measurements?
What can we say about?
Or what do we know about Fourier measurements?
Okay.
Do we know anything? It's pretty open.
Yeah, that's good. So, okay, so let's go back to the. Okay, so let's go back to the. Okay, so let's sort of go in between. All right, so for Gaussian measurements, we know a lot. It's pretty much, we kind of got it collectively. There are a lot of measurement models that sort of sit in between Fourier and Gaussian. Things like random diffraction patterns. Together with Yutian Zhang and Qing Chu, we worked a little bit on random convolution, the short-time Fourier measurements. In that regime, it gets harder to prove really sharp results. Like the math gets an order of magnitude harder. But you can still prove things. And so we have kind of a partial picture. Now, when you get to the Fourier model, this is the most important one. Yeah, because usually when you're doing this, it's because there was a Fourier transform somewhere, right? And you know, if you can solve this one, everything gets easier. This one, there are a couple of things that you can try to say about it. So one is you can try to say things about when the problem is ill-posed, well-posed, right? There are classical results on that. There's also a big kind of recent literature looking at how this changes if you put different assumptions on the signal X. You know, in some kind of science applications, the target is sparse, so it's sort of thinking about how sparsity affects things, et cetera. And there actually is a fair amount of progress on sort of figuring out the landscape of uniqueness. There's a nice survey. I mean, there have probably been developments since it, but there's a survey by Hasibi and Eldar on precisely this question. And yeah, there are a number of math signal processing papers that have been written. So that's for uniqueness. Now, for computational recovery, this is really hard. And it's sort of a combination of two things. One is if you look at the best practical methods for this, they tend to be things that have a little bit of the flavor of Douglas-Ratchford splitting, ADMM. They tend to be kind of local in nature, have bad minimizers. If you look at the bad minimizers from far away, they kind of look like combinations of these symmetrizations. And so it's a very tantalizing problem because you see enough that, how do I say? I wouldn't tell a student not to work on this, but I wouldn't tell a student to work on this. So I think that's about where we're at as a field.
Thank you.
Sure.
Any more questions? Okay, let's thank the speaker again.
Okay, thank you.
There is a tea break.